this video, I'm going to describe gases at low pressure, ionization, and breakdown processes. When it comes to gases at low pressure, there are 4 different regions of interest. It's the ohmic region, where free electrons from cosmic rays drift from the negative to the positive electrode, and the current is proportional to the voltage. Then there's saturation, where the voltage is high enough to get all the electrons, and there's no increase in the current. And lastly, we have the exponential part of the curve, where electrons they gain enough energy to ionize the gas molecules, and avalanches can happen, ultimately leading to a breakdown between the electrodes. But how does these electrons gain energy in the different regions, and what is mean free path? So the energy of the electrons is proportional to the number of electrons times the electric field strength times gamma. Let me try to draw gamma here. Okay, so this is gamma, and this is proportional to, so let me write it a bit better. This is proportional to, again, the number of electrons times the electric field strength over the pressure. So pressure plays a role here, and I'll talk about that later. But what are all of these things? Well, the number of electrons pretty much says itself. That's how many electrons we got in the medium. The electric field strength, we know that from before. The electric field strength is proportional to the voltage over meters. And this means that if we have an electron here, and it's some point in space, and then we have another point in space here, then the energy or the potential between these 2 points is described by the electric field. So you can basically say it's how much energy is gained from traveling from this point to this point. It's another way of describing it. Then we have the mean free path, and the mean free path is that, let's say we have a path here. So this is our path, and then we have our electron, and the electron is traveling through this path here. Then the distance, or the mean distance it has to travel before it hits some gas molecules, that's the mean free path. So it tells us something about how crowded the medium is. And this is also why it's proportional to the pressure, or inversely proportional to the pressure. Another important coefficient is the Townsend coefficient, or ionization coefficient. And we denote that by alpha. So this is alpha. And alpha is proportional to the new electrons that are created. So new electrons here in the direction of the electric field. In the direction of the electric field. So per centimeter in the direction of the electric field. So this is kind of pseudo notation, but I hope you're with me. So how can we describe this in another way? Well, let me try to draw it again. So it should be in the direction of the electric field. So if the direction of the electric field is like this, it's only along the x-axis in this case, then we have our electron, and our electron is traveling in this direction here. And then the electron, it hits something, it hits a gas molecule, and the gas molecule creates some new electrons. This is actually ionization happening. And this happens over 1 centimeter in the medium here. So this is 1 centimeter. Then this pretty much describes what the ionization coefficient is. It's how many electrons are, how would you say, created in this path here. And lastly, the Townsend coefficient, or ionization coefficient, is proportional to the pressure, or inversely proportional to the pressure. So if we have our Townsend coefficient here, and we have pressure here on the x-axis, then it looks sort of like this, like a bell curve. And why does it look like a bell curve? We have 3 regions of importance. We have here, here, and here. In this region, there's not a lot of pressure, meaning there's not a lot of gas molecules to hit. So we cannot really have ionization. There's not a lot of ions that can be created in this region. Then we have the sweet spot in the middle. There's just enough gas molecules to cause ionization and create more electrons. And then we have too crowded region here where the pressure is too high. There's too many gas molecules, so the electron cannot gain enough energy before it hits another one. And it needs a certain level of energy before it can knock out new electrons from the gas molecule. But how does this knocking out of electrons happen? And that happens by a process called ionization. So what is ionization? Let me start by doing a drawing here where we have a high voltage node sitting at a negative potential, and then we have over here positive electrode, ground reference, sitting at a positive potential, and then we have an electric field going from positive to negative. So the way that ionization happens is that when we have an electron that travels from the anode to the cathode and gain enough energy. So let me try to draw it. We have an electron here, and the electron travels along its path. So the path D here. And when it travels along this path, it hits an atom. Let's draw that in green. And this atom doesn't have a charge. It's not ionized yet. But when the electron hits it, and it hits it with enough energy, the energy that exceeds the ionization energy, then it will knock an electron off the orbital of this atom. So the same electron as from before, and then a new one is created, if you can say that. And this is called ionization. And if this continues to happen, where each free electron knocks out an electron, then we have ionization even further. And in the worst case, if you can say that, instead of just having a leakage current, we can have a breakdown from the avalanche. But how does this look between these mediums? Well, it looks sort of like this, where we have teardrop shaped, where on the tail of this we have some positive ions, gas molecules, positively charged, and in the top, or the head here of the teardrop, we have the electrons. The electrons are traveling faster than the ions because the ions are heavier, so they will drift slowly towards the negative electrode, and the electrons here will drift faster towards the positive electrode. And the way that these new electrons are created can be described by this equation here, where the number of new electrons is equal to the number of electrons initiating this ionization times the natural exponential function with Townsend coefficient ionization factor as before times the distance d. So what it describes is that when we have an electron starting here and that hits an atom, creates even further electrons, how many of these electrons are created? And we see it depends on the number of electrons to begin with, the ionization coefficient, and the distance here between the two electrodes. But when does this avalanche turn into a breakdown? Breakdown happens because of something called secondary emission, where a positive ion drifts back towards the cathode, hits the cathode, and releases an electron. If the number of electrons from this is high enough to sustain the discharge, creating avalanches upon avalanches, then we will have a breakdown between the two electrodes. Now, how can we describe this secondary emission with an equation? Before we do that, we need to understand how this drawing relates to the equation. So after the gold emission here, we have an electron that is released, and that electron can go on and create more avalanches. So after crossing this gap here, D, we have an electron that has traveled all the way here and created some new avalanches. And that means that we have from before the number of electrons to begin with times exponential, natural exponential, to first Townsend coefficient or the ionization coefficient times the distance here. So this means that we have one electron that initiates it, and then we have, if we subtract that one electrons, then we have after this a number of ions that are created. So if you remember from before, we had the drop here where we had some electrons and we had some positive ions, and these positive ions are proportional to the number of electrons, and we have -1 because this is the first one that initiates it. And these positive ions, they go on and hit the wall, this wall here, and the probability for these positive ions to release a new electron is proportional to secondary Townsend coefficient. So we can write that the number of new electrons is proportional to secondary Townsend coefficient times the number of starting electrons. And then we have this term here that describes the new number of electrons from the gold emission. And this is the probability, by the way, for new electrons to be created. But what is the mechanism behind this for breakdown? So when does the breakdown occur? The breakdown occurs if we group these two together. Then we have secondary Townsend coefficient, and then we have the natural exponential to first Townsend coefficient times d -1. And if we define this as q, then q is our loop gain, meaning that it tells you how many new starting electrons we have here after each avalanche. So this is our first avalanche. The positive ions hits the wall, and then when we start the next generation of electrons, how many do we have? This is what Q is described. Is it, if it's larger than before, then we have a self-sustaining mechanism, and Q is larger than 1. If it's less than 1, then the avalanche will die out. So this is the self-sustaining condition for the breakdown to happen. We can also write it more detailed, because it's the same as describing that the new electrons are equal to the number of starting electrons, and then we have each generation here. So we have the first generation plus the second generation, and so on. So you can see how that if Q is larger than 1, it will be self-sustaining, and we will have a breakdown between the two electrodes. It should be noted that these mechanisms, the Townsend mechanism, are only valid for gases at low pressure, meaning below 5 bar per millimeter, At higher pressure, it's the streamer mechanism, which I'll describe in another video.